Hello, good afternoon. My name is Mark Tian. So I'm from Confluent. And today we're doing a presentation on Apache Kafka Confluent event streaming system. So you're very welcome. It's my first time here in the Singapore office for Rakuten. I've spent quite a bit of time with your colleagues up in Fukuoka, who are big Confluent users and build event streaming systems. So today we're going to talk a little bit about enterprise streaming platform architecture patterns. So if you're interested in distributed systems, event streaming systems, how to deploy them across different data centers, and keeping the whole thing going despite failures and all that, that's the subject of today's talk. Most of what we're talking about today concerns Apache Kafka. Actually, everything applies to Apache Kafka, and every now and again, there's one or two Confluent things as well. So I'm a principal solution engineer with Confluent here in Singapore. I've been with Confluent for about 4.5 years. And my colleague, RG, is also here. So he'll be coming around to say hello during the talk today. It'll be 60 minutes. I won't run over. We'll share the PDF afterwards. If you're interested in any more details, then I'll skip over some of the detailed slides. So I'm hoping everyone's fairly familiar with Apache Kafka, what it's all about. So it fits into this world of open source distributed systems. You know, Hadoop kind of led the way, and then we had Spark and Kafka. They all fit into the same ecosystem, and they're large-scale data processing platforms, distributed systems built on Java. There are lots of reasons why you want to distribute your Kafka cluster. The most obvious one is prod_dr, right? We're all used to prod_dr. But now we're doing things like stretching across multi-region, stretching across cloud providers. Sometimes we want to exchange data with partners and things like that. And these are all reasons that we look at our distributed systems. There are a bunch of design principles that we're interested in. The most important one is the RPO. We don't want to lose data. Now, there are different failure scenarios, everything from your VM going down to your data center blowing up, right? So you can't deal with all situations and prevent data loss, but you aim as much as possible to not lose any data for most failure scenarios. We call that RPO 0. If you can get an RPO 0 system, you're doing pretty good. RTO 0 is how long it takes to get your system back up again. So we always aim to have RTO as low as possible. You know, seconds is challenging, but certainly minutes should be possible to fail over from prod to DR, or from Hong Kong to Singapore or Taipei or something like that. Okay, there are various other ones. So tooling support and scripts. So we help our customers a lot to just build all the scripts to do failover and fail back and get all that stuff working. Okay. Platform recovery, how to automate. You shift from scripting to automation slowly, bit by bit. You say, well, this bit works okay, so we can chain these scripts together, automate it a bit more. And you move towards a goal of having a fully automated failover, if that's what you want. Client recovery is nice for Kafka because actually the client already is pretty much transparent. It's able to fail over automatically between systems. So Kafka has a very big client. It's what we call a thick client. It has a lot of functionality built in, and it actually helps you a lot when you're thinking about multi-data centers. Cost optimization, you know, we all have budgets. We have to stay within budget. So it's nice to sort of roll out a Rolls Royce with you know, machines all over the place and data centers everywhere, but you have to think about what it's all going to cost. And your long-term strategy. Whether the company's moving towards cloud, moving towards fully managed, moving towards containerization in your own data centers, whatever that sort of strategy is, we'll move to that. If anyone wants to ask me questions, just stick up your hand and ask. It's fine. Otherwise, we'll share contact details afterwards, and you can ask questions by there if you want as well. So a very quick recap. This is the sort of a standard Kafka slide, lots of boxes, lots of arrows. The key thing is Kafka systems are able to cope with failures, right? It's a distributed system. So you usually start with 3 VMs, VM 1, 2, 3, broker 1, 2, 3. If you knock over broker 3, the other two notice within a few seconds, and they reconfigure and they carry on business, and there's a brief pause, right? So we've done a fair bit of testing with your colleagues up in Fukuoka, and we've done failover testing, where we take down one broker while there are lots of transactions being played into the system, and it continues okay, just as Kafka is designed to do. And there's a fairly the underlying architecture to all this is distributed systems architecture. You have leaders and followers, you have replicas, partitions, all of these sorts of things. So working on the assumption that we know that Kafka can cope with a failure on a simple Kafka cluster. This would be a simple Kafka cluster with 4 brokers, 1, 2, 3, 4. then how do we take this idea and make it bigger and think about multi-data center and cloud providers and all that? So these are some of the subjects we're going to look at today. So I'm going to use these sort of pictures to illustrate the different architectures that I'm thinking about. So I work a lot with banks and credit card companies and fintech companies all across Asia Pacific. And we always kind of end up with one of these. So this is data center 1, data center 2, data center 3. And within a data center, we just have VMs, so a Zookeeper or a Kafka. Let's just focus mostly on the blue ones, the Kafkas, right? And the dotted line shows you the cluster. So this is Kafka 1, Kafka 2, Kafka 3 with a dotted line. So it's a 3-broker Kafka cluster in 3 data centers. So a stretch cluster, right? For organizations that have 3 data centers close to each other, you can do this and it works fine. And it's actually great for Singapore because Singapore is small. The round trip times, the milliseconds between here and here is usually very, very low. We see as low as 0.0, 0.4, 0.5, like half a millisecond, which is really very, very fast. It's good also in Hong Kong. It becomes more problematic in Europe and the States and all that, where distances are bigger, where the fiber is not so good, where you have all sorts of lesser infrastructure than you have here. But there's lots of these sorts of things running in Singapore, and it works perfectly fine. There's no issues. So an Apache Kafka can be distributed like this. Then a variation on this is, well, what if you have two data centers and you have a machine room? So often in the office, you'll have some sort of a protected machine room. You'll have some racks available, and you can kind of put something in the machine room. Does that help? And the answer is actually, yes, it helps you a lot. Being able to do this, where you just put one single node, would be a Zookeeper in your machine room, which could be like in your head office. It could be in a cloud provider. It just has to be reachable. That's all. It doesn't run that much. Single service, small JVM, but it actually gives you much more automation whenever anything goes wrong with DC2 or anything goes wrong with DC1. By just having this, we call it a tiebreaker, having a separate tiebreaker that's unimpacted by power loss here or here. Actually, your system has much higher resilience. This gets you much closer to RPO 0. So this is also popular. I have some of the banks here. They have 2 data centers in Singapore. One of them, some of them put this one in Hong Kong. Some even put it in London, and it works okay. So this one doesn't have to be close. It just has to be available and online, and it works okay. So this is called a Zookeeper 2.5, where the 0.5 is just your machine room. There's just a couple more of these, and then we start getting into some of the other ways for this stuff to work. With Kafka systems, an active passive prod DR, so everything's connected over here. All your processing is happening. Your producers, your consumers, all of your apps are running in prod. But you want to have a passive DR. So this is no longer an active setup. Now we're active passive, and we're able to do a failover. So when infrastructure says we're doing a DR test, we want to fail everything over. Can we do it? And the answer is yes, we can do it. But to do this sort of thing, we need something to synchronize prod and DR. There's a few options. Mirror Maker is an Apache open source project, and it basically just sucks all the data out of this and pushes it all into here. It consumes and it produces. Okay, we have an enterprise version of Mirror Maker. It works in a very similar way. There's lots of sort of fine print when you're using these types of services to connect prod and DR. This was popular maybe 2-3 years ago. It's not that popular anymore because these tend to be quite big VMs. They need a lot of resource. Okay, and then the last one is bidirectional. This one's unidirectional, just standard prod DR, very popular type of setup in Singapore and in Southeast Asia. Same idea though, using Replicator or Mirror Maker. And the last one is from multi-data centers, the idea of a hub and spoke. So, you run a business across lots of different financial centers in Asia Pacific. So the whole idea of being able to consolidate from various centers into, say, Singapore or into Tokyo or other major processing centers, this is also the sort of architecture that we set up. And we refer to this as hub and spoke. So there's a lot of decision points on exactly, what type of architecture to choose. So if you're in the business of choosing this, then have a look at the PDF afterwards and go through it. And we're gonna go into some of the pros and cons of these different ideas over the next few slides. Okay, so geo-replication. We have many customers that do global, right? They have systems in the US, in Europe, and in Asia Pacific, and they want to replicate between them. There's no magic. It still takes hundreds of milliseconds to send data, cross-continent. But the idea is you need your system to be reliable and to be usable for the consumer. So you have to maintain ordering. You have to maintain delivery guarantees. You just have to make sure that your system still has the service quality, even though the distances are much further apart. There's a lot of bridge to cloud. Organizations running a lot of stuff on-prem, and they just want to run services on cloud, whether it's a full Kafka system on cloud or just consumers and producers running on cloud. DR, of course, and various other ones. Increasingly, we're getting into data sharing. We have companies there are various companies that either use Apache Kafka or Confluent customers, and they say, well, you use Kafka and you use Kafka, so why can't we just share together externally and produce and consume into each other's system? So, we have one in Bangkok, and they're moving away from FTP, and they're moving over to using Kafka to exchange data between their different organizations. Okay, so let's page through a few of these different and introduce some new technologies as well. So the stretch cluster that we talked about. So 2 data centers in Singapore. I wanted to just deploy active so that my application can run either side and it's able to automatically switch between the 2 sides. So on a much bigger scale, this is what the full system would look like. If you had like a mission critical production system that you want to be always on, able to tolerate failures, able to participate in DR tests, you end up with something like this. It's complicated. There's a lot of VMs. So these boxes are VMs, still a Zookeeper, still a Kafka. We can see we have a Kafka cluster here. The big thing about this is it's dual zone. So every time you have a data center, you ask the infrastructure people, are you single zoned, dual zone, or tri-zone, right? And that means that they're able to separate the VMs and the storage and the power and the cooling into different zones. Often it's different floors, different halls, something like that. It's a really important question for distributed systems. How's your data center set up? How many zones do you have? So a dual zone system like this is nice because we can put half of the stuff in one zone, half of the stuff in the other zone. And this is a stretch cluster. This is kind of like the prod DR we saw before. And it means that we can take one zone down, we can roll it, we can restart all the VMs, and the other zone will continue automatically. So without any interruption to service. This is a very nice thing to have because infrastructure want to keep rolling VMs and restarting and security patching and all of that, right? You don't want to take your system down. There's one complication here. We have this observer. These are like standby Kafka brokers. So this is a Confluent thing, not an Apache Kafka thing. But we have this idea of standby brokers that are able to step in if they're needed. And to do this sort of thing with 2 zones, you do need to have a standby observer Kafka broker that's able to step in. Otherwise, this thing pretty much runs with no intervention. So infrastructure can take down a whole zone. So we're rolling the system on a Saturday, and you can say, well, my microservices will be fine. They will pause briefly for a few seconds when this zone comes down and it reconfigures to the other zone. And then when the zone comes back online, it pauses for a few seconds again while it reconfigures. And then these standby nodes basically step out again and go back into standby mode automatically. The role of Kafka observers is because we want to have a min in-sync replicas of 4 for data durability. So it needs to have 1, 2, 3, 4 available. We don't want to spend a fortune on brokers. So the idea of the observer is it's just sitting there as a standby. It's receiving data all the time from the other brokers. If we take down this whole zone, we only have 3 brokers left. It's not enough for producers to continue. So the observer steps in to act as the 4th broker while it's needed, and then it meets in-sync replicas of 4. System is able to continue processing again, and then it steps down. When the second zone comes back on, it has 6, 1, 2, 3, 4, 5, 6. So it meets the 4, it's able to continue, and the 2 observers can step out. You only need these for a 2-zone system. Yeah, and this is actually one that I'm working on with one of the banks here at the moment, because they want a system where they can shut down either prod or DR, and it reconfigures. It's not actually automatic for prod or DR, but they can fail it over. But they want to be able to shut down a zone without calling in the application development team and saying, shut down your microservices. They find it very problematic to try and coordinate infrastructure shutdowns and application shutdowns. Okay. So that's the. What if you only have a single zone? So supposing you're running in a data center and they say, well, we've no halls, we've no VMs, we just have a whole bunch of racks. You have no zones, so you have to make it work like that. So it's a single zone. You put everything into a single zone. You'll notice we have no observers this time. And basically here, we obviously can't take the whole zone down because you're going to bring your whole cluster down. That's not going to work, right? So all we can do is take down 1 or 2 nodes at a time. And then we switch over to instead of thinking about zones, we think about tolerance. What's our fault tolerance? And the fault tolerance is we can have 2 of these down, or we can have 2 of these down, but no more, right? And having a node down tolerance of 2 actually makes your system much safer, because when infrastructure are restarting your system, they shut this one down and patch it. And then if they shut this one down too quickly, you would have 2 down for a short period. And that could cause an outage if you hadn't configured it to think about what's my node down tolerance, right? So we like to do a node down tolerance of 2 for this, node down tolerance of 2 for this. And then you can safely restart one by one, and your application is not impacted. Very brief pauses of a few seconds for each broker, that's all. Okay, so this is actually pretty common, even though a lot of data centers, like Equinix type data centers, they do have multi-zone. Often organizations don't buy multi-zone, they just buy a single hall, and you don't really get the choice to do this. And then the third one is cloud providers. So we all know cloud providers have 3 availability zones, right? And this is the perfect fit for distributed systems. So systems like Kafka and Zookeeper and Spark and Hadoop, they're really built for 3 zone systems. That's why you have 3 brokers. That's why Zookeeper needs a minimum of 3 nodes, all that sort of stuff. And it means if we take down a zone, we take out 33% of the system. We still have 66% of the system. Kafka is fine with 66%. You don't need to intervene with anything, right? So this is the perfect sort of setup. And if your own data center provider can provide you with 3 halls or 3 zones, then you can mimic this, set up the same thing, and then you don't even need observers. You don't need standby brokers to step in and keep your system running. And this is also cheaper. There's just fewer nodes, easier to manage, fewer scripts, less complicated to run. So we have quite a number of customers that run self-managed Kafka or Confluent on cloud providers, and they just set up racks and distribute nodes like this, and it works perfectly fine. So this is an always-on RPO0 system. Okay. All right, that's the end of those sort of big diagrams for a while. So let's talk a little bit about some of these other ways of doing this. So Replicator or Mirror Maker, it just basically synchronizes one Kafka cluster with another Kafka cluster, consumes from one, produces to another. There's an awful lot of details in the fine print about exactly how that works on things like delivery guarantees, offsets, transactions, consumer offset syncing. There's a whole ton of details that are sort of obscured in this one box. So one is open source, Mirror Maker 2. One is the product that we provide. The main reason why we see anyone using this is if you have a DMZ, right? Supposing you're on private link in AWS, you're on private services connect in Google, and these are both private networking. How do you make them talk to each other? So often you will have connection back to on-prem data center that's able to reach both networks. So you have a DMZ. You put your replicator, the DMZ, it can reach both systems. It can replicate between the 2. That's the key reason we still see using this type of service, a push-pull synchronization service. Other than that, there are other options available. So hybrid architecture, on-prem to cloud, region, failure, disaster recovery, data sovereignty. If you need to move data between different countries and you have different regulatory obligations, so data coming out of Indonesia or Korea, the regulations are different. So how you handle PII, how you tokenize is quite different. You can actually build that into Replicator. So you can attach jars to Replicator to tokenize and say, okay, plug out the phone numbers, the IC numbers, the addresses, tokenize them and replace them as the message is flowing through. So you're sort of tokenizing on the fly. Governance, cluster migration, various other reasons why you would use Replicator. Let me just keep an eye on time. Okay, so the next idea is cluster linking. So in a similar idea, but now we're just linking from cluster to cluster. So this is new technology. This one's a Confluent technology, but it's really worth having a look at to see, because I think this is really it's a shame this wasn't sort of built into Kafka from the beginning. You have a source cluster and a destination cluster. For anyone that's from the database world and you're used to database links, it's the same idea as a database, like an Oracle database link. My background is all Oracle systems. And the whole idea of this is that you create a cluster link to link one cluster to another. So that could be Singapore to Hong Kong or Singapore to Jakarta. It could be a cluster running on AWS linked to Google. It could be from an on-prem cluster linked to a Confluent Cloud cluster or etc. Any two, not entirely any, but most sort of Kafka clusters can be linked together like this. The destination would need to be Confluent. The source can be all sorts of stuff, as long as it's Kafka. And the idea, like in your standard prod DR type thing, all your applications, your producers and consumers are running on your source cluster. You have a standard set of topics, and then you basically decide which topics you want to mirror over to the destination cluster. Okay, you don't have to. You can do the whole thing if you want, or you can just nominate certain topics and send them over. Okay, and we're going to be looking at this in a bit more detail as we go through. There are all sorts of clever things that you can do regarding bidirectional data sharing by automatically putting prefixes. So all these distributed systems really love the idea of prefixes. So rather than mirror a topic called clicks, which could be website clicks, right, as people are navigating through your .com. If that's landing in a Hong Kong cluster, you can automatically prefix it to Hong Kong and mirror it to Singapore. And then as people are navigating over here and the data is being saved in Singapore, that mirrors over and is prefixed by Singapore. So a lot of these distributed systems infrastructures love the idea of automatically putting prefixes before topics, because it opens up lots of options around creating data sharing patterns like this, right? We don't want both to write to a topic called clicks in two locations at the same time, because there's latency and it creates all sorts of problems with delivery guarantees and offsets and duplicates and things like that. So we want to try and keep it unique. Okay, so let's step through how we would use something like cluster linking, because it helps to understand a little bit of how something like this works. So supposing we have our old cluster, so our current cluster, and we have a producer writing clicks in, and supposing it's writing 1,000 per second, right, into a topic. And we want to move over to a new cluster, and maybe that's in Taipei or something on AWS. How do we go about it? So create a cluster link. Nothing happens yet. All we're doing is establishing a link from Kafka to Kafka. It's authenticated, it's encrypted, but we're not sending any traffic over the cluster link yet. We're just saying we're going to link to this cluster because we're going to send data to it in future. Okay. And then the next thing is we create a mirror topic. So it's another command, create mirror topic. We can say asterisks for all the topics or just clicks for one topic. And it will basically auto-create the topic over here with the same config, right? So if it's same retention, 7 days or 1 day or whatever, same number of partitions, max message size, all that is carried over. And then it just consumes everything from source and produces everything over here with exactly the same offsets. So it's just mirroring the data over so far. It also does the consumer groups. So as your application is connecting and basically producing clicks and consuming them out to an analytics page or whatever, the consumer group is recording, what's the progress? How far behind are we? So it actually synchronizes the consumer groups as well, because the reason we're doing this is we're going to move our consumers over here eventually. So we need to think about how we're going to do that. So after you've migrated all the consumer groups over to here, you basically switch the consumers to the new one. So our application is still writing on the old cluster. Now, because we have data mirroring coming over here, we know that we have the same data going into both. We can just shift our consumers over here. We don't need to run consumers on source anymore. And then we stop the producers. So turn off the app, and now we have a bit of downtime, because we do have to turn off the app on one cluster and then start it on the second one. So we turn it off on the source cluster, and we run a command called a promote. And a promote just turns this from a mirror topic to a normal topic. It goes from read only to read write. We're saying that we're going to start writing into this one now, right? So everything related to cluster linking is basically creating a read only mirror of the data on another cluster, right? And then after we have done the promote, this becomes writable, and then we can just start our producers on the new cluster. And now data is only flowing into the new cluster. There's no data flowing into the old cluster. Our consumers are already over here. They don't know where this data came from. It doesn't matter to them anymore. And basically we have done our migration. So that's how cluster linking works. It just establishes a link between Kafka clusters, and then topic by topic, you create a read-only mirror of that topic on a remote cluster. This is a very different approach to using something like Replicator. Remember earlier I showed Replicator and Mirror Maker, and it sits as a box in between. So the data gets consumed from one into Replicator, and it gets packaged up and sent to the next one. None of that happens here. So this is broker to broker. There's no deserialization, there's no decompression. It just actually takes the binary data from one, pulls it across, and drops the binary data on the other server, which is why compatibility is very important on versions and things like that. So it's actually super efficient, super fast. There's no infrastructure sitting in between the two. So it's a very nice way of synchronizing systems together. And you can use it for DR, right? It's nice to think that you can just set up a prod system and then cluster link to a DR system and sort of go through the steps. So the way it works is if our prod goes down, no producers, no consumers, we had mirror topics. This time, instead of running a promote, we run a failover. A failover assumes basically that your source system is gone, right? That it's no longer reachable, like this, right? So the difference between a promote and a failover is our source is gone. Don't try and even connect to prod because it's offline entirely. So it means just set these to read write, no matter what their status is, because we want to resume our application as soon as possible. So instead of running a promote, we just run a failover and basically start using our second system. Okay, we're a little over halfway through. So and a nice thing with cluster linking is you can chain topics together. So you could bounce from you could have an application running in Singapore that's producing into a topic. Then you can mirror that to Hong Kong prod, and say have consumers there doing something, and then you could chain that onwards to Hong Kong DR. And so you can keep chaining mirror topics on as much as possible, including hub and spoke type patterns as well. So it lets you really think about sharing data into other locations. Now, the benefit of doing this is just for local consumers, keeping your application simple. Often you don't want an application that's, say, running in a Hong Kong data center to be connecting back to servers in Singapore. There are various reasons why you may not want to do this. So it makes sense just from data governance point of view to mirror your data rather than having cross-region connections for your applications. Okay, and you can fan it out. So in the same way that you can chain topics, you can have multiple mirror topics for a source. So we may have a cluster running in Singapore, and then we're mirroring the same data to Japan and to Hong Kong at the same time. Now, they won't be exactly the same because the distance to Japan is further. So there's more milliseconds latency on this cluster link than there is on this one. So this will always be slightly ahead. But the idea is we still have our ordering. We still have our delivery guarantees. We still have all that important stuff to know that this is a reliable, usable copy of this data. It's a true mirror of the original data, right? So you can fan out as much as necessary in order to do this. And you can fan it out, and then you can sort of fan it back in again into an aggregate type cluster. So we do this with mostly kind of retail organizations, insurance organizations that have a lot of business operations across Asia Pacific, where the businesses operate separately, but we need to aggregate the data back to headquarters again. And just trying to do this in a sensible, straightforward way is the goal. So that was cluster linking. And then very briefly on multi-region clusters, which is the last type. So the idea, when I talked about doing DR tests and failovers and all that, like when you go from prod to DR and you run a failover, you do have to tell the application team, okay, now reconnect to DR. It's a separate cluster. So shut it down, change your config to point to DR and start it up again. Sometimes that's not possible. Sometimes infrastructure doesn't have central visibility over all the applications, or it might be just a more diversified team, and you can't just fail everything over. Sometimes you want just to reconnect automatically, right? Because it's just how applications have been set up. So we have one customer that I work with. They operate between Singapore and Taipei, and they really have no visibility of applications coming online and offline and who controls them, because there's lots of different partners and all that. So they just want to be able to infrastructure fail over to Taipei, and then all the applications reconnect automatically to Taipei. And then when they fail back to Singapore again, they reconnect automatically. This is a pretty complicated thing to do, like conceptually, but there's the way of doing is this thing called a multi-region cluster. And we've already looked at it briefly, this whole idea of standbys, and the reason these are called observers. You can take this concept to the entire cluster level and say, like, Taipei is all standby, right? It's all standby brokers, and we're able to fail over entirely to Taipei and step back event. So you can use this whole idea of standby brokers in various ways for a full cluster, or just to make up a missing broker in a cluster. That's a multi-region cluster. So those are really the four sort of multi-data center techniques. So in Singapore, prod DR, low latency, we can stretch a cluster, keep it nice and simple. Applications will run in either data center depending on when the latency is. A lot of organizations do this in Singapore, and it works well. Replicator, there are various reasons. If you're purely in the open source world and you like Mirror Maker, that's perfectly fine. If you need to put your data in a DMZ, or you need to change any data as it flows, then this is a good idea to use. It uses a fair bit of VM infrastructure usually because it has to do a lot of work on the data. Cluster linking is sort of point to point. Very low overheads on infrastructure and things, but it's a Confluent only thing. And then a multi-region cluster is where you want to be able to fail over without touching your applications at all. I don't want to stop and restart anything. I just want them to flip over automatically to a remote site. Then you would use this idea. So there's a whole bunch of details. I left all these tables in. So if you're interested in the RPO and RTO for all these, please dig up the PDF after this. And there's also a whole bunch of sort of considerations, right? The different reasons that you would want to use these different techniques. So they're all included. If you're interested, please look for the PDF. Lots of details. Okay, so that's largely the multi-data center stuff. I just want to touch on a few other topics, right? Fairly small things. So for those that may not know, like I never really introduced our company Confluent, but we're basically the company founded by the creators of Apache Kafka. So we only really do Apache Kafka. And a fair bit of what we do is just putting on different services and features and things onto that are not available on Apache Kafka itself. I'm going to touch on a couple of those. Some of these, and I'll say like if these in the open source world or in the Confluent world. There's a whole bunch of things within the Kafka broker that are sort of added on and compiled and that we put in. Things like if you use access control, it can be a bit hard. So we've changed it to role-based access control and added in auditing and things like that. You'll increasingly see this whole idea of being able to use an object store for Kafka. So as you know, when you write data into a topic and you say, keep this for 7 days, it keeps that data for 7 days in a topic on each of your brokers, and it kind of mirrors between the 3 brokers. Now, if you only ever use 3 brokers and you sort of stop one at a time, you never really notice this whole problem of balancing on a distributed system. But if you have a 10 broker cluster or 15 or 20 broker cluster, the biggest I've seen is about 300 brokers, then brokers can be coming online and offline all the time. And this becomes really problematic because when you have a large number of brokers, your data is distributed across the entire cluster, and you have busy topics and quiet topics. You have big topics and small topics. You have all sorts of different shapes and sizes of data flowing through the system, so it gets unbalanced. It's a natural phenomenon on a distributed system. But one of the funny things about Kafka is you're really only interested in cached data. If it's working properly, the producers write it in, consumers get it out within milliseconds, or even maybe within a few seconds. And actually, it's only storing the data in case anything goes wrong. You don't need the data for normal daily operations because everything is being served from memory on your brokers. So it's a fairly high price to pay to keep all of this data online all the time, when in fact, you only need it in a very small percentage of cases. And that's where the idea of using an object store comes in. Why not just take most of the data from your brokers, put it out in an object store? If you need it because you're rebalancing or you have a failure, you can go and read the object store. You don't need to pull this data from all the brokers. So this idea of multi-tier storage and brokers only carrying probably 10 to 15% of the data that a normal Kafka server would carry, and you move 80% of the data down to an object store. And in situations where you need it for rebalancing, for failures, it may be a bit slower because it is reading the object store, but actually you have a benefit of having much lighter brokers. You don't carry as much data. And this is much more thinking like Kafka brokers as being like an in-memory system, and everything should be served from in-memory for a well-tuned system. By using an object store like S3 or Google, I've forgotten the Google Cloud Storage, I think, and Azure also have an object store. These are pretty much infinite. You can push as much data as you want out to these. And that means that you can think in terms of topics having much longer retention. So some financial services customers keep data for months or years, just so they can retrieve it in the order that they need. It depends. Also, some insurance companies like the idea of just having infinite storage. On availability, these are we've talked a fair bit about multi-region clusters already. If you don't use Kafka Connect, it's really recommended. So this is all open source. It's part of the Apache Kafka project. The idea that you can just connect to databases, or connect to S3, or connect to files, or connect to FTP, or connect to messaging, and just stream in and out of topics rather than having to write code for everything. So you shouldn't have to write like a Java program that connects to Postgres that basically selects from a table and produces to a topic, because there's already a connector for that. In the same way, you shouldn't have to write a connector to insert into an Oracle database. There's already a connector for that. And all this stuff is open source. So often the whole Connect ecosystem is ignored or not known about. But if you're connecting to enterprise systems, not microservices, but any enterprise systems, take a look at the connector ecosystem. And stream processing is basically the idea that you can change data as it's flowing through the system, right? If you're producing data in at one end, say into a credit card application, and then you have a whole bunch of different consumers for that. If you find that the consumer needs to write a lot of code to use that data, then that's really a case for stream processing. It's preparing the data for the consumer. The data should be in the right shape for the consumer as it flows through the system. Otherwise, what tends to happen is you end up with a lot of code sitting outside your system, sitting in consumers, in microservices. And if anything goes wrong, only the application development team has visibility for that. And it often happens that they're doing the same thing, right? So you have one microservice that looks at it and says, well, I don't want JSON, I want Avro, I need a schema, I need a key. And then the next microservice, same problem, next microservice, same problem. So it makes a lot of sense to prepare this data and stream process it so that the consumers don't need to do much more work on this before it goes out. It leads to a more robust system. It's less brittle because you have more centralized processing for the data. That's the idea of stream processing. There's two ways of doing it. One is Java. There's a Kafka Streams library, and it just has an API for streaming data. How do we think about data moving continuously? And the other is this KSQLDB, which is also open source. And this lets you do stream processing using select statements. So everyone everywhere knows how to do a select statement because it comes straight out of ANSI SQL. But it happens to be a very neat fit for stream processing as well. And they all sort of fit together, right? So if you a whole bunch of core Java developers and they love writing, Java, then fine, use Kafka Streams. But people that are less comfortable with writing Java or prefer .NET or Python or whatever, then it's better to look at KSQLDB, and you can embed this, or you can run it directly. You can run it via REST API, various other things. And then there are sort of the lowest level that will just use the produce and consume API. Okay, just have a few more slides left. Just watching the time. The way the whole sort of picture fits together is if you're sending data from data stores or from messaging systems or files, use the Connect ecosystem. Your standard microservices, Java, Python, .NET, Go, use the clients for these, and they all connect to your Kafka system in the same way. Stream process where you need to, where it makes sense, right? So try and have less happening out here and more happening in here. And then when you're sending data to downstream systems, then use the connectors wherever you can, especially if you're inserting the databases. This whole JDBC sync. And just mirror a topic into a database table. This stuff has been around for years and it works very well. I'm going to jump over a few of these fairly quickly. Some of the problems with using Mirror Maker, circular replication. I think we've covered a fair bit. The very last section here is just a little bit on hybrid. When you're running on cloud and you're running in VPCs, your networking becomes a lot more complicated because you have to think about, do I have connections coming in and going out, and can my on-prem connect to these? And from sort of the simplest type of architecture is the complications of private networking when you're running on cloud providers. So if you're on-prem, how do you connect to services that are running inside a VPC or a private link or a private services connect? And then if you're bouncing onwards to other services, how do you connect these various private networking setups together? It can get fairly complex. The example shown here is, suppose we're running a database on-prem. We want to mirror database tables into a Kafka topic so that every time there's an insert or an update, say a Postgres or Oracle or SQL Server, we want to produce into a topic in Kafka so that we can have an event-driven application that's just consuming from activity happening on a database on-prem. How would we go about something like this? So we could use Connect, to mirror the database table into a Kafka topic. If we have to go through now this is using the Confluent Cloud system where we have to use 2 VPCs. So we sort of go through, use a HA proxy to go through the custom to your own Rakuten VPC, and then onwards to a managed service. And then we can further simplify this, right? We can think about going directly, using a VPC peer, something like Direct Connect. We're able to connect directly into a VPC peered transit gateway or private link cluster. So this type of thing is fairly popular. You can stage stuff on-prem, right? So if you're running a Kafka cluster on-prem, you can stage it and then mirror that using something like cluster linking or replicator or mirror maker all the way into your fully managed service. And the final one is, of course, you can sort of you can just run your Kafka cluster in your own VPC and just run clients on-prem. So either Kafka Connect clients or producers or consumers, and they're just connecting to your Kafka cluster. So all of these types of architectures are in place. Every time I talk to organizations and we're sort of doing solution architecture, everyone has a different combination of how they want to connect stuff together. The biggest one that's happening now is I'm running in AWS Private Link and Azure Private Link, and I'm running Google Private Services Connect. Can you connect them all up for us? We want to mirror data between all of these. And that's where things get much more complicated, I guess. That's today's talk. So that was streaming platform and architecture patterns. So this is the first in a series of 2. The next one's on 7th of December. We have a few minutes for questions. If anyone if there's anything that you'd like to ask, let me know. And we can also follow up on email. My colleague here, RG, will take questions as well. You're welcome. All right, I hope that was helpful. Thanks very much, everyone. It's a pleasure to be here. We look forward to the next session on 7th of December. Thanks very much. Yes. Yes.